So good morning, everyone. Welcome to MGM course, Mathematics of Generative Modeling. And in the last class, I discussed RNN, a recurrent neural network. So this was in the last class. We discussed recurrent neural network. And in short, it's called RNN. And we saw that it's meant for sequence problems. So this means natural language translation. Okay, it could be used in speech processing, music processing, and so on. Stock prices even. So basically, any data that has some sequential nature, RN could be employed. Hence, it's because of these recurrence structure, it's also a autodigressive process in the sense that from x0 we get x1, then we get x2, and then we get x3, and so on. So in the same class, there is an extension. It's called, we usually call them Seq2Seq models. So Seq2, but we can use the same ideas like we have. So Seq2Seq models. And then there is a further extension to this, which is called attention. And that is mostly useful when you're doing natural language translation. Okay, so basically it's also called encoder-decoder model. Okay, so we will see this in detail, why it's called so. And we will also see the concept of attention, and that will be later also used in transformers that we will do today. So we will first start with this sequence-to-sequence model, and we will see where it's used, how the processing will be done, basically how the loss function will be built, and then we will introduce attention, and then as a final step we will also describe transformer. So what we have seen so far is depending on the problem, we may have certain models. So for instance, we may have, let us say, a one-to-one model or many-to-one model. So input goes in, and then you have some output here. So this we call it many-to-one. So this could be seen as a classification problem. So many pixels can go in, and then I need to describe what would be the object in the image. So that would be classification. It could be many text goes in, and then I may have to describe the sentiment of the image. So that could be also seen as many-to-one model. And we can also have like variants of these. So for instance, one-to-many. So one-to-many. So I have one input, and then it produces a set of outputs. So that could be a image captioning problem. So I introduce an image. So this is image captioning. So I input an image, and then a bunch of text that acts as a caption for the image. Caption, which will be a sequence of words describing the image. And we may also have many-to-many. So something like this. So this we have also described this in the last class. It could be, let us say, a sequence labeling problem. So sequence labeling, or describing each word, let us say, whether it's a noun, verb, or adverb, adjective, and things like that. And so this is a many-to-many case. So this is many-to-many. This is one-to-many. And this was many-to-one. And similarly, we can have also another variant of many-to-many, but it's with slight delay. So something like this. And then so we have set of inputs, and then we have set of outputs after that. So this is many-to-many, but with a delay. And the first input goes in completely, and then the output comes in later on as a one full step. So this is also many to many, and this is exactly the case where what is needed for language translations. So this is translation or summarization. So text summarization, so I give a lot of text and then ask it to make a summary of that. So essentially here it will be a long input, and then I will expect a sequence of text, but it should be much smaller than the input, obviously, because it's a summarization. It could also be used in question and answering. So for question and answering, yeah, I will come back to that. So basically the input will be a sequence that describes a question, and output will be a sequence that describes an answer. Okay, so here we are expecting that the answer is also in couple of words. Okay, or it could have been that answer is just one output, okay, true or false, yes or no, or just one number, then it could be treated as many to one in that case. Okay, so these are the possible these are the possible cases. Like you may here, if I'm saying image, but it could also be some other data. Okay, so basically you can extend this to variety of applications. Okay, I have just given some examples here. So this covers quite a bit of examples. So what we have seen is that we have RNN, but then for let us say specifically for this type, where we want to do translation or summarization and so on, we can focus on these sequence-to-sequence models, and which are also called encoder-decoder model. So today we will focus on this type, this specific type of model. So in a sequence-to-sequence model or encoder-decoder model, we have the concept of a encoder. So encoder takes set of inputs. So let us say it's a source or input, and then from the encoder it goes into decoder. So decoder is also some you can think of these as RNN cells, and then this produces some target or output. So this is our decoder, and this is our encoder. So as you can see, this follows this many-to-many structure, but then we have divided this input part into encoder and output part into decoder. Okay, this is what we have done. So this allows us to model this in a slightly different way, and also allows us to introduce something called attention that we will see. So the encoder is responsible for processing input sequence. So the whole goal of the encoder is to process input sequence, and then decoder is responsible to generate output sequence. Okay, that's the goal of encoder. Encodes the inputs, and decoder decodes the input. And this may sound similar to what we have been doing in let us say variation autoencoder. We have, or autoencoders, we have encoder-decoder model, and now we have something similar going on here. So there will be a latent space also in this case, which we will believe that it encodes the whole input sequence in a nice way. There will be some latent space that will encode that. Okay, so the similar philosophy also extends here. So because of this, hence sequence-to-sequence model is called, hence sequence-to-sequence model is called encoder-decoder model. Okay, this is called encoder-decoder model. So that's another name. And the submodules that we have here, these are submodules. This could be implemented in the architectures that you may be, this is something your choice. It could be RNN based framework. So we have seen RNN, so they will input, and then there will be HT produced, and then that will be used. Then there is another set of inputs. So this could be based on RNN. It could also use LSTM cells that we have seen in the last class. LSTM cells here. Similarly, for this guy, you have choices of using RNN, LSTM, or there is a variant of LSTM. It's called GRU, gated recurrent unit, which is a simplification of the original RNN, and it works as well as LSTM. So it's a simplification, and then basically they figure out few things are not needed in LSTM. They were redundant, and hence you can also use something called GRU. So this is the idea that overall the model is encoder-decoder model, and within that you can use different set of. Let us assume that in this case, assume that encoder and decoder are some type of RNN. By the way, what we will see also as a later part of the course today is that this encoder and decoder model is also used by transformers. The only difference is that the way it encodes looks very interesting, and the way it also has a decoder is also a very interesting architecture. Okay, it's quite different from RNN LSTM, although some of the ingredients like attention and masking and all this is used, like which is also used here, but it is quite a different, looks quite different, and overall it looks quite different. And this is the one that's behind GPT 3 and 4 that's currently going on. So basically these are like pre-trained decoder. So they train it on a lot of data, and then they have seen a lot of data, and then they use it for the next token prediction. So this is the technology behind all this. So if we now look into this encoder-decoder model now, and try to kind of for a small example, we can try to see how this overall works. So let us try to see an example. So a small structure first. So let us say this is our encoder. Okay, and then what happens as a step is that this is our encoder, and then we have the decoder, and then we have some start token, and then this is our final hidden state. So in a sequence-to-sequence model, as I said, we encode the inputs. So in this case, let us say the input would be the battery is dead. Okay, and this is our encoding, and then here also it goes like this. So overall the structure is like this. So as I said, once we have this inputs, we discard the outputs here. Okay, we don't need these outputs. Okay, this is a sequence-to-sequence model. The whole sequence goes in, and then a whole sequence as an output comes out. That's why it's called sequence-to-sequence. So basically there are no outputs produced, no intermediate outputs. Okay, so in this model we have no intermediate outputs, and we have one encoding state. You can put an arrow here. So this is also one form of an state, although I've written it in a different form. So this is our encoder, the state that takes this. Remember, these are these h t minus 1, right? So all this t, and finally it gets some form of h. Finally it gets the final ht gets stored there basically, and this final state is then used along with some start token, or it may not be any start token. Okay, let us say. Okay, I mean usually we will use that some start token, and then when along with this encoding, it will start producing the, let us say, translation. Okay, so the first word in the translated sequence, and then the output of that first word in the translated sequence will go as an input, and then it will then produce the next word in the sequence. So in the decoder form, obviously there is no input to be given as such. The previous output will be fed as an input. So there is no, as such, there is no input, explicit input. Obviously for the decoder, it starts with something, starting word is fed in the next time step, and then starts producing some other word, and so on. Okay, so that's the idea behind the decoder. So this is the overall model we have in hand, and what I will do now is go into a little bit of more specific of what I have outlined here. So I will do it here. So I will draw the similar figure, but now with a little bit more detail. We will work on a little bit of more detail on this. So this is my first cell, my second cell, third cell, and fourth cell for this example. And then, as I said, there is a encoding, and then we have the decoder cell. So let us say we have decoder. So here, let us say the input we have is a vector representation. So usually we have to create a vector representation for the word, okay, because the neural networks only understands vectors. So as I said, this goes into trace, okay, basically no output, and similarly the battery is the input for that, the vector representation, and then you have is, the word is, and then the vector representation of that, and then you have the word dead and a vector representation of that, and then all these intermediate outputs, they go in trace. Okay, so from there we get a encoding, and this encoding is later on used here. So this is, let us say, our some start token, and then this starts producing some output. So let us say we are looking into English to Hungarian, because it will bring its own nuances. So let us look at this as an example. So here it will produce this. So I don't know Hungarian, but yes, I hope what we are writing is correct. And this is A K K M U L A T O R, and then finally it has the N token. And here, as I said, these first output will be fed as an input. So in this case, so this is our input, and then the second output is now fed here. So in this case it's AZ, and then the third output will go in here, and in this case it's, and for all this, obviously their corresponding vector representation goes inside, and then here also the vector representation of accumulator. So finally it produces an end, and that's where it will stop, okay, the translation. Okay, so this is how the translation happens from English to Hungarian. So this is our obviously decoder, and this was obviously our encoder. Okay, so here what we have seen before, this way of training is called teacher forcing. So if you can recall, teacher forcing is a way to train a model when to produce next word in a sequence. So you already have that sequence and you are training a network. So if it produces an output, then we want that output to be the correct output from the sequence we have. So in this case, if it produces something other than this, then we will force the network to update the parameters such that it learns to produce this next time. Okay, similarly, if this word goes in, then what we know is the correct word is already AZ. We know that. In case the network doesn't produce AZ, then we will force the network to update the parameters via gradient descent. That's called the training. And then updated weights, we will expect that it will learn to produce AZ. So this way of training is called teacher forcing. So this is also called a conditional language model, because you are producing the output is conditioned basically on the encoding. Okay, so the way your output will be produced depend on what type of encoding is used here. Okay, so So that's why we will also call this a conditional language model. Okay, so basically the output is conditioned on output conditioned on encoding, which itself is conditioned on the inputs that it received. So the decoder here, when it produces, obviously it has to learn a way to select the most probable word in the sequence. So these are the most probable words that it's going to produce. Similarly, these are the next set of probable words after it has seen the previous word. Okay, so we can construct a loss function, because eventually we have to train this model. So like we have done in the previous class as well, we can create a probability loss function basically in this case. So log of the probabilities of this, a negative of that, so that these losses will be combined. And as you know, in all supervised learning methods, you have to define a loss function, because that is how, with the help of loss function, you know when the network is doing badly or doing good. Based on that, you will update the parameters. So hence, describing a loss function is essential, obviously. So we can define some sort of loss function here. So for instance, we can define the log likelihood, I mean the log probabilities basically. So these may be defined as let us say minus log of y hat, which is the output here of this word lemerult. Okay, so I hope you can see this. So this is the probability that what is the probability that this word will be predicted. Similarly, we can say the same thing, log of y hat of az, and so on. And based on this, we can kind of combine all of these to make a complete loss function that will be used in the training. Okay, so basically the output that the decoder produces, and the output that that is expected, that will be compared in the loss, and then that is something that will help us to train these networks. Okay, so so some of the remarks are so basically, again, yeah, so the decoder output is compared with actual output, because we already know the sequence, right, the correct translation, and that is used for training. The encoder and decoder are trained end to end, meaning when I'm training, then I will train until the encoder. And why is the case? It is the case because there is also a possibility that the way encoding was done was not correct, and that is the reason why your network is failing to produce the translations. So it's essential to also do a back propagation to compute the gradients and use that to update the weights of this model. Okay, so in this case, these guys have no role, so there will be no back propagation going on here, but you will certainly do back propagation here and here. Okay, so here you may not do, let's say, unless the embedding itself you want to introduce a weight there, and you want to learn the on the fly also the embedding itself, further embedding of your input itself. But if you don't do that, it's fine. So you can do a back prop like that, and basically it will follow like that. Okay, so basically the back prop can happen end to end from the last time step of the decoder. So this is our time t, let us say, and the sequence produced is xt. So we can say this is the output terminal sequence, and then here these are the input terminal sequence, and we can train this end to end. So I will write this here: encoder and decoder are trained end to end. Okay, end to end means from end to the beginning, basically. Okay, that's what it means. So obviously encoder is also trained because it may not have done the correct encoding. Okay, Okay, so I guess that's with this. So this is more or less settled. The only thing that I skip for the moment is the proper training of this. So basically, the next steps involved are these building these loss functions and then summing these loss functions and then using some Python library, let's say, to do these backpropagation steps. So you can see these implementations and then you will see how these models are trained. But this is the main idea behind encoder and decoder. But what is missing from here is something called information bottleneck. So what is happening here is that for all the inputs, what will be used in the end is this encoding stat that will be fed in, okay, along with the start token, and the question is how good this will be in encoding all the previous context or the words in the sequence and so on. Okay, and that's where the idea of attention comes in. Okay, so the attention idea says that you have produced some hidden representations before, and using those hidden representations coming from these blocks, you had output. Obviously, output will go in trace anyway, but you have used that hidden representation to propagate like this sequentially from here to here, then here to here, then here to here. So in this process, you may have lost some information along the way, even if you use LSTM. Okay, you may say that I said the same thing when I went to LSTM, that there may be a memory issue when I go from here to here to here. So LSTM will fix that to some extent. So let us say I use LSTM cells, and then there is this context vector that goes for the LSTM, and that will help propagate the encoded information correctly, or in a sense like improve basically. Okay, the correct is a very strong word. Like it will improve on this, basically prevent loss of memory held by this hidden state. So LSTM also could be used, but still we believe that even LSTM, even with having LSTM, encoder has a lot of pressure to encode information from, especially if the input sequence is very long, then there is a lot of pressure on encoder to capture all the context in this one state. Okay, and hence the idea of attention is says that why can't you directly use this hidden representation? Why do you wait for this to get updated and then use it at the end? Why can't I use this directly here, okay, as an input here? Similarly, why can't I use this directly to produce the second word of the sequence in the translated sequence? Okay, so that's the idea of an attention. So that's where I will go next. So as we have seen, language modeling is a very challenging task because of a lot of relationship and also alignment issues and so on. So machine translation, so to motivate a little bit on why I want to do attention, I will just give some examples of what are the challenges. So let us say we have words like this: the battery is dead. Now the translated form of this is so in the language we have these alignment issues. So and also a couple of words get translated into one word in translation. So there is something called alignment issue. So for instance, is dead means and in the same word, I mean, or if I want to create some specific different examples, so he got away with cheating at the exam, and then the translated would be okay. So this is the translated one. I may not be able to pronounce it well, so I'm not saying that. So here if we look up a little bit, then this got away with is represented by this one word. So there is this issue of many to one, where many gets mapped to one. There was also this case here, but in this case even three words got mapped to one. So many to one. This is another issue. So that's why language translations is a bit difficult. And it could also be the other way, one to many. So C is fluent in English, and this is okay. So in this case, it seems that fluent got translated into this. Okay, so this is one to many. So these are various issues when you do language translation and you want to learn this because of these different variations you have. There are also some structural challenges. So for instance, so the battery is dead. Can be written in two different ways also. Okay. And it is also another way is that we can write like this. So both are correct. That's what I was trying to say. So there's also a possibility that same word can be written in different ways. So these are the challenges that you have. Multiple orders are also possible. So okay. So multiple orders are possible, and so before even going to the attention that I said, what I want to discuss is this way that we are producing these translated words, and if our model has learned, then what is the good way that I select the next words in the sequence. Okay, so what happens here, if we look here, is the way we will kind of predict. Okay, so let us say given a sentence, I have two different ways to do the translation of the same, right? So we may be dealt with the choice of which one to select, and this problem is about selecting among multiple options, let's say. So then we may be led into branches. So for instance, from here I may be having two possible choices, and this is these are the choices that are done in a sequence. So in some sense you may not be able to predict, you may not be able to see it in a long term. So this means that you may go with a greedy approach, that I will take the one that has the highest probability right now. Okay, but greedy approach may not necessarily be the best approach, as you know. Okay, it could be that you could have chosen second one as the second most probable one, and then it would have been a better choice compared to it would have been a better choice in the sense that the total cumulative loss would have been lesser than going with the strategy of taking the best one possible as a next sequence. So these are some challenges. Also, one has to, so there is concept of beam search, and so that's what I will briefly discuss. So let us look into an example of beam search. So let us say we have a decoder step, which is so which gives me a probability distribution and produces, let us say, the letter the, and then I have to feed in the vector representation of that comes from here, and from there I get a probability distribution to pick the next word, let us say SIP, and then similarly now the word SIP goes in, and then I may predict, let us say, again I get a probability distribution. From there I pick the word docked, let us say. Okay, or there was one more step. So basically has, let us say, so this is the SIP goes in, and then we produce, let us say, so let us say we have probability distribution here, and has or sailed and then 0.6, 0.4 are the probability distributions, and then using let us say has, which has the highest probability, and we produced the word docked. So if you look into this sequence, then we start with a start token start, and that produces the. So usually sentences start with the, let's say, and it depends on what I'm going to translate. In this case, we're doing it in reverse way. Let us say we have some the French a word encoded, and then we are producing this decoding, which looks like this. So we have the first word the, and then so this encoding that you see here, that might decide the initial word in the sequence, which could be the. Okay, so you may wonder why it should start with the. Okay, this is what encoding will play a role. Okay, so that gives you the highest probability, let's say, to pick the is fed in, and then it goes through this trained network, let's say, and it gives me a distribution, probability distribution. Let us say I build all the vocabulary of the world, okay, and then it goes through some form of a softmax. You can see this is, let us say, classification problem. So in this vocabulary, I have the else, if, okay, person, like all the words in the dictionary, let us say, and let us say has, sip, dot, sailed. Okay, so we can view this as one big vector with this. This may not be like the optimal way. So let us say one of the possibilities is this. We put all this, and then there will be, let us say, softmax, and then it will produce a, let us say, some form of a probability distribution. And then in this, it will say that, okay, the next most probable one having seen the is, let us say, the SIP. So it will produce, let us say, a vector of probability distribution, and here it may say that SIP has 0. And other has 0.01, 0.05, and so on. So this is the probability distribution we are talking about, like this. This is how we see probability distribution, and from there we will pick, look at the probability distribution, and we see, okay, 0.7 is the highest, and that corresponds to the word SIP. So I'm going to select SIP. Okay, so this SIP is selected, that's how, and then it goes in and is the input, and then again it produces the probability distribution. So let us say it, in this case, let us say in the third step, SIP goes in, and then let us say has probability 0.6 in this case now, in this time step. So it produces 0.6, and sailed has probability 0.4. Okay, so, and then others are very less because it's already like very, yeah, so 0 something. Okay, so let us say the important thing is, like, as it sees words more and more, the choice of words that follows will get very limited. So in this case it will be like either you go with this or this. There is no other possibility. Let's say, for example, okay, so then you have a choice of picking has, or you can terminate this translation with saying sailed. Okay, but since has the highest probability, you may prefer to go with has. So then you will pick the has, the 0.6 probability, and then you produce has, and then again you will look at the probability, and then there will be somewhere docked word probability, which seems to be the highest in this case. Let us say somewhere 0.7, 0.9, or whatever. Okay, and that's where you will end. And basically you also supposed to produce kind of an, so there will be one more. So since the sentence looks complete, the probability, so there will be also a start token, and an end token can also be put in here. Okay, so we have end. So after seeing all this, it seems that the end has the highest probability, that we should pick the end token now as a final step to end the sentence. Okay, so in this process of producing next word in the sequence, a natural question is, should we always go with a greedy approach where we pick the highest probability? Okay, so greedy approach, pick the word with highest probability at next time step. Okay, next or current, I believe current maybe. So pick the word with highest probability. So this is greedy approach, but this greedy approach may not necessarily be the best approach. Okay, because it may be the case that the second one may produce more relevant translation. Okay, more interesting translation of the word. So how do you kind of model this, okay, as a loss, let's say, because this is even during the training itself, you may have to kind of decide all this, because you are trying to build some loss function based on this. So so this loss functions kind of has to also see maintain certain options, not just go with the greedy approach, but maybe look at multiple options, and then once it sees multiple branches, and then based on that it may be able to decide better which was the good choice of word to choose there. So there is a concept of something called beam search. So we can, it is still greedy, but the point here is that yeah, so it is still a greedy search, but the point here is that we will keep the most interesting branches as we go along, the window of some branches, rather than picking just the most probable one. So if you pick most probable one, then there is no branch, there is just one branch basically, and no other branches. But what we want to pick is, also I want to go in the has direction branch, and I also want to go in the sail direction branch, and I want to see in future, okay, and then combine the total probability, and then I see and decide which would have been a correct path to choose. Okay, so with this in mind, we can create a greedy approach. So I can demonstrate that here with a small example. So in this case, for this example, let's say, so we start with start token, and then we produce the, and let us say all this is with probability 1, and then also with probability 1 we predict SIP, and then we have a branching here. By looking at this, I could have followed the hash branch, or I could have followed a sailed branch. Okay, so I have so this is, let us say, 0.6, and this is 0.4, and I arrived at hash branch, and hash branch again could have gone into docked, or it could have gone into sunk, and let us say these are with probability 0.55 and 0.45, and then here we have sunk and sunk here, and here again let us say we have two branches. So here I believe this is home, sailed home, and here this is sailed away. So this is 0.1, and this is 0.9, and this is 0.4, and so on. Okay, so if you see in this example, then we have also written down the probability values. So if you have followed, let us say, a branch, so we are computing the probability values, so higher will be better. So if we follow this branch, let us say, so if we compute the probability values of this branch 1, 1, 0.6, 0.55, then what we will get, it will be 1 times 1 times 0.6 times 0.55, and that gives me 0.33. And if we have followed the branch the SIP sailed home, let us say, so in this case the cumulative probability values will be 0.4, 0.9, and that comes out to be 0.36. Okay, so higher is better. In this case we are computing the probability values, so 0.36 is higher. Okay, so the fact that you choose this branch because of the greedy strategy, you thought 0.6 is the highest, I should go with this, but that did not lead you to highest probability in the end. Okay, so the ideal one was that you should have followed this branch. Okay, so obviously you can say that this branching can explode essentially. Okay, for long sequences there could be many branching happening, and then would you be able to track all these different branches? Obviously we cannot. So this will grow exponentially in computation. So but what we can track is the two best ones, let us say. So we call it, let us say, a beam search of order. So basically how many branches I want to maintain. So we can say in this case, let us say I track two top branches. Okay, so for instance here I see this branch has so far given me the highest probability, and this branch is the next highest, and then out of this I will maintain this branch. Okay, I will maintain this branch, and here also I will see, so far I will maintain as I go ahead, I will maintain this branch as a whole, and I will keep dropping these two. but I will keep sure that I will have 2 branches until one of them terminates. Okay, so this is the idea behind something called beam search. So what I have described is the idea behind beam search. So here we can keep a window of 2, as I said. So maintaining a branch, a beam width of 2 in this case. Okay, so as I said, I'm not writing things in words. Like maintaining all the branches is not possible. If we have, let us say, 20,000, 30,000 words, then maintaining all branches for all of them is just not exponential. It's going to be exponential cost. So we'll maintain just to highest probable one. Okay, or in general, the people go for let us say a width of k. K is variable. In this case, we choose k to be 2. Okay, so and sometimes what happens is that one of these branches may get a bit longer, and some of the other branches, let us say you maintain only 2 branches, but even there, one branch may get very long and another branch may get very short. So there may be a bias towards a shorter branch, okay, rather than picking a longer branch. So then in the loss functions that we describe, we should normalize this with the length of the sequence. Okay, so the length should not play as a bias. So hence we will describe a loss function basically that so shorter sentences may be chosen in favor of longer ones in a beam search. So in this case, we may look at the normalized score. So if we define a score like this, will be 1 divided by t. So this is the normalization we're talking about, number of words total. So here we define this log of probability of wi minus 1 w1. So this is the normalization we are talking about. So this is the loss function that will be used, okay, with the normalized one, and we use some sort of beam search with certain width, and overall this could be used. So now coming back to introducing an attention is what I have described before as well. Is we will move to attention now, and so basically we have the problem of information bottleneck. So in this means, as I've also described a little bit earlier, is that we have encoding, and then we have a decoder steps, and so this is, we call it a information bottleneck. Okay, so it is supposed to cramming all information about source. Basically all information about the source, and then longer the source sequence, greater the loss. So that's obvious. If it's longer, then there's no guarantee that encoder will be encoding all those contexts in a good way. So the idea here is that rather than throwing away all these informations that we have produced before, why can't we use it in some form? Okay, and that's the idea behind attention. So that is what I'm going to now describe next. So we'll use this board. So what I will describe now is the attention mechanism, which is introduced in this sequence-to-sequence model, which will be later used also in the transformer case. So Okay, so this is the model that we have. So I have given so the basic idea, as I said, behind attention is that we are going to use this H1, H2, H3, H4, which was previously not looked at directly. They were looked at via the final state as an encoder. So now our goal is to use this. So we have this these f functions defined here. So this f functions they work on let us say if I have to compute um, so I will define this f function here. So these f functions are like this. F of hi sj is v transpose of 10 h of whi plus usj. Okay, so the way this f function works is that they take this h1 and then they take this this sequence s, okay, and then so we can see here that we have a final output s0, let us say, from here, so let us say, and the f function, the s is the so is this one in this case. So and then it will be used to with h1 here and to compute these f scores. So f of h1 s0 will be this guy, f of h2 s0 using that formula will be this guy, and so on. Okay, so this is how we compute these f values. So these are basically f of h1 s0. So this is f of h1 s0. This is f of h1 h2 s0. This is f of h3 s0. This is f of h4 s0. Okay, so this is how this is used. So in combination with this and these that we have the hidden states. So this is how this f is used, and then it goes via softmax to create some form of a probability distribution. And then with the softmax we get these four values. So this is alpha 10, alpha 20, alpha 30, and alpha 40. Okay, so and then this is then used to compute the context vector, which is Cj alpha ij hi. Okay, so this is the I. Okay, so with this we can so we have these HIs computed already, these HIs, and then these alpha i's are computed after the softmax, and based on this then we compute a context vector, and this context vector is then concatenated with the this is concatenated with the embedding of the input token, which in this case will be the start vector. So this is concatenate context vector Cj with embedding of start token. Okay, so basically this idea is now repeated. So what will happen is that once it goes there, and then it will produce some output, let us say. So this is like y hat 1, and that we produce as there, and then from here it will also produce some hidden state, let us say s1, and then this s1 can be again used with in the next time step, and this s1 will be so the way it will get used is, again, we follow the same steps, but now we compute the scores with s2, sorry, s1. So then we again go back and attend to these words, and then these scores that we will compute f, and now again it will now change to f of h1 s1, f of h2 s1, f of h3 s1, f of h4 s1. It goes through softmax, and then the alpha values that we will have now will be alpha 1 1, alpha 2 1, alpha 3 1, alpha 4 1, and using those alpha values and then these hi values that we have, we compute the second context vector. Okay, so this context vector then again gets concatenated with this and concatenate it with the C2, let's say, okay, the second context vector, and that is then used to produce the next word in the sequence and so on. Okay, so if we look into these context vectors, then these are nothing but a feed-forward neural network. So feed-forward neural network with the parameters W and U, and these are obviously shared parameter network, and then these get updated basically. So we define a loss function, and then we see how this loss is, and based on that we will update the weights of these and these. Okay, so basically these weights tell us that where should be put more attention in this source word basically. So that's also trained, okay, because these weights are there, and that will try to learn which of the word is the most important in the prediction of the second word in the translated language. So we are giving a full attention to all the words in the sequence, in the input sequence, and that should help the network learn much better compared to just letting the encoding layer kind of encode all the information that it had seen in the input sequence. Okay, so this is the idea behind attention mechanism. Okay, so I will provide the link to some of the implementers there, and you can see for yourselves, but the basic idea is that's it. Okay, there's nothing more here. So this is iterative process, so you keep doing this iteratively, one after the other. You keep creating this context vector, and then you keep updating these. Okay, so that's how the attention works. So um, so um, So with this, I will move to the next part of this lecture, which is the transformer network, and the benefits of I can point out the benefits of attention. So the benefits of the attentions are that it overcomes information bottleneck by enabling the decoder to look at scores. So this gives a significant performance boost in sequence-to-sequence task. Okay, so these are the benefits of the attention network. So then we may move to transformer.